Okay, we're talking about the final. The last thing we're doing is right around the corner, and I posted this practice test, so I was gonna go through it, kind of talk about what I think is important out of it, how I would, approach some of these problems, and kind of the thought process that I think would be required to be successful. This is my dog. Her name's Murph. And I guess she wants to watch today. Um, so I'm going to spend a second talking about kind of these general topics. So, um, I don't really care. I'm not going to ask you guys about like R and S configuration of stereo centers, but I do think that it's good to know, when have we created a stereo center? When would we have multiple products? What does it mean to have a stereo center? What even is a stereo center? Um, so being able to recognize like within a mechanism, hey, we went from something that's sp2 to sp3, and that sp3 carbon has four different things attached. So in this case, this is a chiral molecule. Um, and then, whether or not it stays chiral or doesn't by the end product can kind of tell us if we end up with one thing or multiple things. Um, we also spend a fair amount of time talking about solvents, so you should be able to classify the solvents based off polar, nonpolar, protic, aprotic, when will we use them in a certain reaction, or if they're being used in a certain reaction, why? Why can we use this? Why should we use this solvent? Um, just be able to kind of get through that and uh, use the idea of solvents to justify reactions. And then I want you to be able to name new functional groups and classify reactions on names. So the way I would kind of practice that is, and we're going to do it as I go through this final practice, is just kind of let's discuss what we've made, what we've used, and kind of the kind of reaction that we're doing. Do we have chemistry terms that would help us describe this reaction? In terms of reactions, we're going to kind of go through these. Each one of these has an example in the practice test. Um, so just kind of understanding these are kind of the biggest ideas in Orgo 2, by my opinion. Besides maybe the LH for sodium borohydride, but all of these other things, enolates and acetal, enamine, all these carbonyl things, cuprates, 1,4 additions, 1,2 additions. Um, this is the heart of organic chemistry, and this is where most of the points is going to lie. And then we have synthesis. We've added a little bit here, mainly the enolate, which is just kind of a replacement for the grignard epoxide. Um, but for the most part, we've been doing fairly well on synthesis, and all we're doing is kind of adding one or two more things. EAS is also a big one, so um, I'm very likely to give you some sort of benzene ring and say, um, functionalize this. Decide what needs to be added first and go through that process in the context of a synthesis. So um, those are kind of the things I might be focusing on when I'm asking these questions. So, and the last thing is going to be a spectroscopy question. So, uh, spectroscopy uh, is a review. It's from the first test, but it's something to go back over. It's something that I want to make sure that you guys are at least reminded of before you leave this
Um,
class.
Dr. Little, are you meaning to share your screen? Because we can't see anything.
Oh, really?
Yeah.
Oh, no. Can you see it now?
Yeah, that worked.
Sweet. I didn't do anything different. Okay, well, I was just talking, writing. But yeah, I mean, you can look at those topics and go through that. This is posted on Canvas, so I hope you already have this in front of you while I was talking anyways. But spectroscopy, it's a review. It'll be good to look at. Um, but it's not going to be as in-depth as it was on that first test when that was the focus, but I do want to make sure that you guys still maintain a lot of the basics. Um, okay. So This was just a reminder kind of what sodium borohydride does versus what LAH does, and how can we apply this to a pretty complicated molecule here. So sodium borohydride, this is a much weaker reducing agent. So that means that it's not going to reduce.
I'm so sorry to interrupt you, but are you meaning to like share the reaction currently? Because all we see is like spectroscopy. I think there might be something.
Really.
Yeah, like it's
Yeah,
kind of like
yeah, try
lagging.
moving the page. It hasn't moved at all.
I have moved the page. I'm scrolling all around in circles.
Yeah, I don't know. It's like it
Oh,
just
that's
says
so
like the
odd.
very top part for us.
Yeah,
Okay.
it's like frozen.
Oh, it's moving fine and it's reflecting onto my screen. Huh.
Maybe like stop sharing for a minute and try to reshare.
We'll try this for the third time. Mhm.
Are you on the Zoom as the same device as what you're using to share?
No,
You
but I'm
might,
screen mirroring my iPad to my computer, which normally works just fine.
okay.
But right now, it's not even seeing the screen mirroring.
Do you have Zoom on the iPad?
Uh, I'd prefer not to do that. That would be a whole thing. Okay. I guess this is already a whole thing. This is great recording. I'm glad that we've got this recorded.
It says like you started screen sharing, but like we don't see anything.
Yeah, it's
Oh,
connected.
okay.
Is the screen
Oh,
moving?
Yes.
oh,
Yeah, that
yes.
works.
It's moving?
Yep.
I have a feeling that what happens is if I change it from one screen to the other screen, it stops working. Okay. Either way, it doesn't matter. Um, so sodium borohydride, it's weaker. LAH is a very strong reducing agent. So sodium borohydride is not going to reduce esters and carboxylic acids. So I'd look at this and I'd say, well, this could be reduced, but that ester is unlikely to be reduced with sodium borohydride. So realistically, what I think I would see is something that looks like this. My pen is freaking out for some reason. That's a great experience. Where I reduce both this ketone and this aldehyde down to alcohols, but the sodium borohydride doesn't touch the ester. The flip side of this is LAH reduces everything. So just like the sodium borohydride, I'm going to reduce the aldehyde and the ketone, but I'm also going to reduce the alcohol. Or sorry, the ester down to an alcohol, which is going to put an alcohol over here as well. So I would challenge you to kind of go through this mechanism, see how I got to this product. Um, why is there an OH here and an OH here? Why did I break this ring? If you follow the mechanism, you should be able to figure that out. Very similar mechanism I put on the last test. Um, and it seems to be a mechanism people struggle with. So I would I would try this mechanism on your own, at least of the ester formation. So, um, really, these reactions, I think it's good to go through the mechanism and kind of think about that. But really, these are things we've seen over and over again. The only thing that's changing is I'm adding a bunch of superfluous things. I'm adding a bunch of things that don't matter, at least in terms of the product that we get. So, THF, that's just a solvent. If you don't recognize it, if it's not something that's seems relevant, if you can recognize other things in the reaction conditions that we can use, then that's what I'm going to use, right? ICTHF, I don't know what that is, uh, but I do know that magnesium turns this Grignard, or sorry, turns this bromine into a Grignard, right? That's what I do know. And then I've got this carbonyl. I've got to be careful. This is called an alpha beta unsaturated, meaning that there's a double bond right next to the carbonyl. And when that's the case, there's two potential places I can add into. I can either add here or I can add here. I know with a Grignard, it's not one of the three. So when I'm thinking about 1,4 additions, really the big picture ones are enolates, things with like sulfur, bigger nucleophiles, or um, cuprates. And then 1,2 additions is basically everything else. So in this case, it's not kind of one of the three big picture 1,4 additions. So it's a pretty good guess that this is going to be a 1,2 addition. It's going to add into the carbonyl directly. And that's going to go here. I broke a carbonyl. I want to reform it, but there's no good leaving groups, so I don't have that option. So what I'm going to do instead is protonate with that acid, and I get to this final product. So it's just a Grignard. We just kind of added false complexity to it. Um, Here's a reaction. This says pH 4 to 5. That just means slightly acidic conditions. So, pH is 7 is neutral, so under that is slightly acidic conditions. So this is just a fancy way to say that I have some sort of acid sitting around, right? There's some mild acid here. So first step is I've got an electrophile. I'm going to protonate it, just like every other mechanism we've ever done. I've got a nucleophile nearby in this amine. The amine attacks the carbonyl. This forms a 1, 2, 3, 4, 5, 6 membered ring. Doesn't really matter where you put the nitrogen as long as you keep count of everything. That's the oxygen, OH, and then there was a carbon attached to this. So I can number these carbons 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so I've got all my carbons, everything's set up right. I just broke a carbonyl. I want to reform it. This is what I just added. This is my best possible leaving group here. Oh, I'm missing a lot. I'm missing a lot of hydrogens here. My best possible leaving group is the OH. So I do have extra protons sitting around. There is something positively charged, so I can do a proton transfer. So I will. I'm going to get this with a methyl. Now I can kick off this leaving group and get this. Now I don't have any other equivalents of nucleophiles sitting around, so I've got to deal with this charge somehow. So I'm just going to use that water or really whatever to take it. So that's my final product. I would say, oh, I haven't been doing this. So the functional group that I form here would be an alcohol, right? So this is a Grignard, right? We would call this reaction a Grignard. We could call it an alcohol formation if we wanted to. It'd be kind of weird to do that, but you can. Um, and just for practice, I would say the functional group I formed here is an imine. So just be aware of that, and
I
be able
have a
to.
question.
What's that?
I have a question about the other problem.
Mhm.
Um, what do we need to know the mechanism for a Grignard formation?
Uh, this insertion of the magnesium.
Yes.
No, you do not. I'm not going to ask you that.
Okay.
Uh, it's a radical mechanism. You can do it if you want.
And would the double bond under the third step form an secondary oxygen?
Would it form a secondary oxygen? Oh, this?
Or not oxygen, secondary alcohol.
You're asking if I would do an addition reaction after this point? Like take this and add it to the acid and then add the alcohol?
Yes.
No. So addition reaction, so it's kind of weird that we teach them so early on. Addition reactions are really slow and really hard to convince to happen. So they don't generally happen like this is just you're just washing it with some acid to protonate something. Like in order to get that addition, in order to add H3O plus or whatever to that double bond, it takes a lot of heat. Um, you'd honestly kick this off before you did anything with that double bond.
Okay,
Um,
thank you.
yeah, I mean that's a good question. Uh, it's not something that's entirely impossible. It's just not the scope of this question, right? You can kind of see what this question is asking for. Okay, so we get to this question, and I don't know what p-toluene sulfonic acid is, right? So this isn't something that was talked about. I wasn't asked to know what this is, but there is something that's kind of key here that even if I didn't know what this is, I could probably tell you what it's doing. It's probably acting as an acid, right? So I know that methanol looks like MEOH, and my pen is funky today. And I know that, for whatever this is, it's some sort of acid, right? And I know enough organic chemistry to not get paralyzed by this. Um, it's nothing crazy. It's probably just going to be the acid in my reaction. So I've got acid, I've got an electrophile, I've got a nucleophile, so I'll just go ahead and protonate it. Second step, this methanol adds nucleophile attacks electrophile. I formed a tetrahedral intermediate. My best leaving group is this OH because this is what I just added in. I'm not going to get rid of that. So the OH takes this proton. Now I've formed a better leaving group here. And now my methanol is going to kick that off. And I've formed this. So the thing about this reaction is that we know that when alcohols add into carbonyls, ketones are aldehydes. That what we're going to end up forming is the acetal. We know that. It's always done it. It will always continue to do it whenever an alcohol adds into a ketone or aldehyde is going to form the acetal. So it's implied that this methanol is the solvent. It's implied that there's excess methanol here. This is very common. You'll see this all the time where that's just implied. It's implied that there's another equivalent and it's going to add in. Then I can use that water that I generated earlier to take that proton, and I end up here. This is my product. I recognize this as an acetal, as I've got two alcohols that are attached to the same carbon. So this is an acetal formation. So that's how I'd think about that. That's how I'd cut through some of the complexity of this stuff and see what's important. This requires you to know what isopropanol is. So isopropanol looks like this. Sodium hydride, well, that's a basic hydride source. So I've got something that looks like a nucleophile. I've got something that looks like an electrophile. My hydride is going to deprotonate my nucleophile. I'm going to get this. Then I can have nucleophile attack electrophile. Always push up into the carbonyl. Tetrahedral intermediate. My best leaving group. This is what I added. This is my best leaving group remaining. This is my best kicking group. I don't have extra protons sitting around because I'm in basic conditions. So this is just going to collapse and kick off that oxygen. And I'm going to form this. Um, then we're going to, I mean, we could probably just use the isopropanol. It doesn't really matter here. We're just going to make sure that we don't end on a charge. It's implied that there's going to be some sort of quenching, that we're going to end neutral. And so that's our product. Let me draw this clearer. So I went from this cyclic ester, right? So this is an ester. It's a carbonyl with an oxygen attached to it, to another ester. So this is an ester, and I would call this a transesterification, right? I went from one ester to another. So that's what's going on there.
Why doesn't NaH add in like another hydrogen where that carbonyl is at the end?
Why does NaH not act like LaH and add into this carbon?
Yeah,
Because NaH is a non-nucleophilic base
okay.
and will never add into a carbon. That's the definition of that term. So the real answer is that sodium hydride creates this like huge lattice-like structure that's like really, really big and actually technically kind of bulky, that just like cannot get into carbons, can only really take protons. But you don't need to know all that. But we know that it's a non-nucleophilic base, which means it will never act as a nucleophile. Will never add into a carbonyl. If it was LAH, we would keep going. Okay, so yeah, that's a good question. It's a question that I anticipate some people getting wrong. It's very easy to mix up the difference between LAH and NaH. That's why I talk about it almost every day. So this is E2 copper lithium. So this looks kind of funny, but I know that I've got an ethyl that's connected to a metal. So I'm going to just assume it's a negatively charged ethyl. And what we know about these copper lithiums is that they tend to do, they're one on the list that does 1,4 additions. So I've got my nucleophile, I've got my electrophile. And the thing is that I can do a 1,4 addition, right? There's a double bond attached to that carbonyl. So it's going to add directly there. That's going to push up here, going to push up there, and we get this with the ethyl added in, and this double bond is here. Then I just broke a carbonyl. It wants to reform. The only thing I could kick off is this double bond in order to make it reform, and I can do that to go pick up a proton. And we end up with this. Right.
Oh, union.
But
So like one of the things that makes these questions seem more complicated is all these like random chiral centers thrown in there, or like relatively complex molecules, or I just throw in things here that don't actually play into the reaction, like solvents and temperatures and stuff like that. Ignore them, pay attention to what you know, and don't go grabbing, don't go reaching. I've seen people add extra steps to a mechanism and actually get less points than they would have if they just do what they know, stay in their base, and get the partial credits they know they can. If you start just adding a bunch of stuff that's wrong, it will make what you've done right seem less right, if that makes sense. So don't overextend yourself. Do what you know, stay within your bounds. If something looks foreign, trust yourself.
What's that reaction called?
What is this?
Like for the functional group names, if you
Yeah,
have to
I
do
would say, I mean, we formed this ketone here. Kind of. This one's a weird one. This one would be hard to say, right? We formed a ketone. We got this is I would it's a 1,4 addition. Um yeah, that's a good question. So I think the better question isn't necessarily like I don't really care that you know this is a alcohol formation, but you should be able to tell me it's a grignard. This one, there's no great name for it other than imine formation. Right? That's just the name we have, right? There's no other name for it. Same thing here, acetal formation. You should be able to say, so this would be a trans esterification, right? I've gone from one ester to another. And really, I would care that you could say this is a 1,4 addition. That's a good question. Okay. So this looks like a nucleophile to me. This looks like an acid. I have something that looks like an electrophile. So what's going to happen here is that, just like always, acids protonate my electrophile. That's step one. Step two is nucleophile attack electrophile. What's important to know in this case is a couple of things. One is in acidic conditions, I'm going to form the more stable carbocation. Things are slower. So I'm going to add into the more substituted side, kick off that epoxide. And because this happens in one step, because I had stereochemistry already established, the only place that this alcohol could have possibly come in is on the backside of that epoxide. So actually what ends up happening is this is very similar to an SN2. So for full credit, you'll have to know that it can't approach the epoxide from the face. The epoxide's coming towards us, right? It's on wedges. So it has to attack from the backside. And since we never lose that stereochemistry, since we never go to a achiral intermediate, sorry, my chair's slipping. We maintain a stereochemistry. We do a backside attack. Then we can deprotonate our final product to get to a neutral product. So I'm going to redraw this whole thing. And this OH is still on a wedge. So the epoxide oxygen always stays on a wedge. Then
She sent my name on there. I was looking for her. I couldn't find her. I should get
This
on there and
goes here.
talk.
You guys might want to check if you're muted or not. So yeah, that's a tricky one. There's stereochemistry involved. If you mess up the stereochemistry, it's one of those things where you're going to lose some credit, but it's not going to be in the world. I'd rather you get the reactions right. That's why we didn't talk about the stereochemistry when we went over this reaction the first time. Now it's the end of the class. Now we're having to start put things together. This is important to see. I have stereochemistry. So this is chiral. This is stereospecific. That means that this is also chiral. I never lost chirality, so I maintained some specificity. Okay. LDA is a big, bulky nitrogen. That's a base. So the only thing I can do is take the least substituted hydrogen. That's my first thought. Then I have this. Then I have this electrophile sitting here, and I know that in basic conditions, it's going to attack the less substituted side. Carbon counting is important here. So I added into carbon 3. The oxygen moved to carbon 2. And I still have carbon 1 there. And I still have this methyl sitting here and this isopropyl that are just hanging out. Then this just says acidic wash. So I have some sort of acid. I don't care what you use. You can just write acid for all I care. But I do care that you're able to protonate it, get it to this neutral product. This is what we've done, right? I'm not throwing in epoxides because I just love epoxides. I'm throwing in epoxides because I think they really get at this idea that there's a difference between acidic and basic conditions and reactions. And that's important to see and understand how that might affect regiochemistry or stereochemistry, right? So
For a question like this that has sorry. For a question like this that has like will we need to specify the chirality for this one? Like, will we need to write something that it shows both, or is that not the focus of this question?
I mean that's a good question, right? So let's talk about that. So yeah, I didn't write this as well as I could have. There is a stereocenter on this epoxide. Where is it?
In the middle?
In the middle. This is the only thing is a stereocenter. So let's pretend like I've designated that as a stereocenter. This one cannot be a stereocenter because there's two hydrogens, right? So, I mean, I do think this is a good practice. I should have done this, right? So if this is a wedge when we get to this point, and the epoxide pops open, well, it's going to stay a wedge, right? The thing is, this is still not a stereocenter, so there's no wedge or dash there.
What about the one attached to the cycle?
Oh yeah. So yeah, this one would make two different products, right? So that's a good point. So this is a stereocenter right here. So you would make two different products. So I would expect you to be able to tell me, like, if I asked, hey, how many different products could you make here? Or would you make just doing this reaction? I would expect you to be able to tell me that this is a chiral center that we made, and therefore it could be either way. Right. I went from something that had no chirality to something that was chiral, and I had no way of defining that. I had no way of directing that. And anytime you go from something that's not chiral to chiral, and there's nothing telling you what side you add to, yes, this could be a wedge or a dash. This could be a wedge or a dash, but it is a chiral center. That's a good eye. Good question. All right. Just gut instinct. I'm going to write OH minus. I've got water here. If this OH deprotonated the water, I just get OH back. And then this is pretty hot. 85 degrees Celsius is much higher than 25 degrees Celsius, which is room temperature. So I see OH with a ketone or aldehyde. I know I'm going to do the aldol. I'm going to take the more substituted proton. And since I don't have a ready electrophile sitting around, I can always assume something's going to react with itself. So I'm going to redraw this. I end up getting here. I broke a carbonyl. I want to reform it, but I can't. So I'm going to protonate it. And then I see that there's heat. That tells me that I'm going to do some sort of condensation. So I'm going to use one of my OHs that I either regenerated or had sitting around. And that's going to do the condensation. And I end up here.
Sorry, another chirality question. Will we be punished for not labeling something as chiral if the final product isn't? Like in the
No.
mechanism, there is a chiral center, but at the end it doesn't, so it doesn't matter, right?
No, I mean, so it actually kind of does, right? Like, depending on whether or not this is a wedge or a dash will actually change whether the ethyl's on top, whether methyl's on the bottom. But like, I don't care that if I'm asking a mechanism question, I'm not gonna care about the stereocenters as much, the stereochemistry. That's gonna be its own question, if that makes sense. Like, I'm gonna make it very clear that I want you to tell me about stereochemistry. I don't need you to be like telling me every step of a mechanism, hey, this is now a chiral center. And like that's not that important to me. I'm going to ask you very specifically what I'm looking for. Um, I would say I mean, this is a self-aldol. And we missed that up here. This is a basic epoxide opening. Or you could say something about it being an enolate addition or something like that. These are all good terms to be thinking about. Sodium methoxide. Again, if this deprotonates ethanol, I just get the negative OET back, so that's not a big deal. 3 hours means nothing to me. This OET matches this, so therefore I won't add into the carbonyl because I'll just kick back off and get the same starting product. So I'm going to take the other route, which is to treat it like a base instead of a nucleophile. I don't have a clear electrophile sitting around, so I'm going to assume it's going to attack another version of itself. This is what I get. Then I broke a carbonyl. It wants to reform. It will, since I don't have extra protons sitting around. So I'm in basic conditions. There's no positive charge. I'm just going to do it straight up. And I get this. This is a Claisen. It's the kind of reaction we did. Okay, so I've got K2CO3. This is a weak base. We've seen this before. This is potassium carbonate.
Dr. Little,
Yeah.
I actually wanted to ask, how can you determine which hydrogen would be pulled off in a Claisen or condensation?
What do you mean?
When two above, the one we did two backwards, we did a double bond that connected to, I guess, what I would say is the most substituted, but I see both of them actually have a most substituted.
So this doesn't have to do a substitution. It will always take the proton between the carbonyl and the alcohol every single time.
Okay, perfect. Thank you.
Yep. I don't care if this is super substituted and this one's not. It will always take the one between the carbonyl. You'll always form, notice this? You'll always form that alpha beta unsaturated. A really fun, I mean not fun, but I won't do this to you guys, but I should think about this in the future. And this is a really good kind of thing to put on a synthesis where you do the self-aldol to form the alpha beta unsaturated, and then you can do a 1,4 addition. You know, that's a common kind of motif, right? So I get to this starting material that now I could do a 1,4 addition onto. I won't do that to you guys, but that's there, right? It kind of is cyclical that way. Yeah, that's a good question. It will always, every single time, always take the one between the carbonyl and the OH to form the alpha beta unsaturated. That's a weak base. And I've got this carboxylic acid. Carboxylic acids are always kind of funky because they could be electrophiles or nucleophiles, right? There's the OH, but also the carbonyl. But then I see ethyl chloride, right? This is clearly an electrophile. So I'm thinking that this weak base is going to be used to deprotonate this carboxylic acid. That'd be my best guess. Because I want to use the carboxylic acid as a nucleophile, because I've got a very clear electrophile. Yeah. This is technically an SN2. If you can just recognize this as a substitution, that's great, right? I'm substituting out the chlorine for the carboxylic acid. We're gonna be pretty flexible with like how you might name a reaction. If the reaction, like if you say like carboxylic acid attack or something like that, like you'll get some credit and stuff for that. As long as you're kind of recognizing what's happening. This is substitution. What if we formed an ester, right? This is an ester. Okay. So those are kind of the reactions. It's kind of the tricks that I might have up my sleeve, you know, throw an epoxide, throw a carboxylic acid, because they're kind of the trickier ones, right? You can add in multiple different ways. You'll probably see a 1,4 addition. Um, you know, LAH, acetals, amines, enamines. You know, we've seen these reactions before. So I'm going to continue to just make sure you know them, just with the added complexity of a bunch of stuff that's distracting, right? A bunch of stereocenters that don't matter, or a bunch of solvents that don't do anything, or temperatures that don't really tell us much. Okay, so we've got several different syntheses, but I'm going to spend my time walking through the retrosynthesis of these things. So um, the first thing I see here is a very clear Grignard separation. So I'm going to go ahead and look backwards, and I'm going to say what I probably had at some point in time was this, and a Grignard that looked like this. Again, we're kind of getting to a point where there's probably multiple ways you could do this. But at this point, I have to think, okay, well, now I have to deal with, you know, this is 3 carbons big. So this group I added by itself, and somehow I added this group. So now I have to think these two things are meta to each other. And this is a meta director, which means that it had to be on first. So that amine, if I'm working backwards, wasn't there. This had to be added first. And then this is how I would break this down. Right? And some sort of Lewis acid. So I'll just AlCl3, it doesn't matter. So that's kind of how I would think about it, right? So the meta director needed to be on there for me to add the amine. So I'd take the amine off first when I'm working backwards. So I'll just kind of do this forwards to kind of show you. So we already have this going forward, and then I'll just, I don't know why I said 2. I'll say to get 1 from this starting material. I had to do HNO3, H2SO4. That puts NO2, and then H2 and some sort of metal will get me to 1. This plus this will get me cleanly to 2. So I just make sure that if I'm not explaining specific transformations, I would put that in the mini synthesis. But for the most part, most of your thinking, most of your time should go with the major bond forming reactions. Okay, so I see something like this. This makes me think, well, I know how to add an amine to a benzene ring, and I know how to add an amine to a carbon. So I'm going to kind of chop off all the extra bits first before I get down to the benzene. So I recognize this reaction that looks like this. And I would have had to react that with this carbonyl. But I've got a problem. That's, you can't have two carbonyls in a reaction. So this would get me here. Sorry, that's not true. This would get me to the imine.
Oh,
And then
okay.
I could use LAH and then
Jay's pretty hungry. Jay's pretty hungry.
who's hungry? Okay. Right. So we got to make sure that we remember our steps with the reductive amination, but that screamed reductive amination to me. So now I think that these two things are para to each other. So I would say I need to put this on second, right? So if I have this, then this would have had to been on first. Or sorry. That would have had to been on with this, right? To do the acylation. And then
Can we just kind of pick if it's orthopara, if it's orthopara in the
yeah,
matrix
for
bond
these
format?
synthesis, since I mean you will get both, but we're just gonna if it's an orthopedic reactor, you can just get whichever one you want.
Also, could you form a Grignard and have that direct the H2N to the bottom and then have it add to a carbonyl?
Could you
Or
form?
BR and then form a Grignard and then have that
Yes.
add in.
Yes. That's another viable route. So another thing that is common and could get you somewhere is to brominate and then turn it into a Grignard, and then you can use that for certain things. You can use that for. So that's a good question. So this is an option. This is what I'm saying. Like there's actually we're getting to a point where there's several different viable things you could do. This is one of them. It's a very common option.
And then and another one would be just adding a bromine to the primary carbon off the chain. Like there's just a lot of routes you can go. And
Yes, you could do that, but be careful with alkylations because you form the carbocation. Yeah, I would actually say this is a really good option. I wish I had kind of talked about it more in class. I would be more inclined to give it to you. But you can add into epoxides and other sorts of things. This actually gives you more flexibility forming that Grignard. So it's often a good way to go. But we can do it this way as well. So we want to protect that carbonyl. And then we need to talk about the formation of one, which is essentially taking these two steps. So one is going to be HNO3, H2SO4. Put a nitro group on. And then we're going to reduce it with H2 and some sort of metal, which will give me one. So that's a reasonable synthesis. There's, again, a couple different ways you could do it. So if you did it slightly differently, I would actually, for those of you that have gotten this far and want to know more, this is always an option to look into. It might make your life easier to do it. But here you don't need to do it. You can just do it straight up.
Professor Little,
What's that?
so when you react the ketone, or I guess it's not a ketone, it's an aldehyde with the amine. Don't you need an acid to catalyze that reaction?
Aldehyde with the amine. Oh,
Yeah,
here?
right
Yeah,
there.
yeah, yeah. Some sort of acid.
Yeah,
Sure.
wouldn't that deprotect the other guy?
No, so you really don't. In order to deprotect this guy, you're gonna like put it in a strong acid and water for a long time. This acidic, I mean, the deprotection is sturdy, right? You have to kind of pry at it. So just doing like a slightly acidic catalyzed reaction isn't gonna get at it. I mean, maybe, but honestly, you probably don't even really need an acid to get this reaction to go. It doesn't
Could
hurt, but that amine is so nucleophilic.
Okay.
could something like NaBH4 be used to reduce it?
Uh,
That's the amine.
this it's way more common that you see NaBH4 or even NaBH, but I'm cool with either.
Okay.
But yeah, these are good questions. Um, again, this is probably some kind of reductive amination. So I'm going to go back. I'm going to think about this being a reductive amination. So probably something like this. So I'll just kind of shorthand this. And that's going to get us to the product. This is P product. These two things are ortho to each other. This is my ortho para director, which means that it had to have gone on first. So I'm going to break this down one more time into this plus this with some sort of Lewis acid. And then we know that we could do something like this to get to this product. So that pretty much explains everything. This could actually be done pretty shortly, right? It's a bromine addition, then the acylation, and then a reductive amination to get the product. So I just saw this. Would you get points off if you showed the WB deprotonating after the substitution? Josh, I don't know what that means. What is WB? Are you talking about here? Weak base deprotonating after the substitution. Uh, okay, I get what you're saying. So if you had done the deprotonation step after the substitution, in this case, probably because you just need a weak base because this is an acid. This is a really strong acid, whereas like a weak base with an amine, which is not very acidic, like that. It's kind of understanding the pKs. It's understanding that that's really acidic, so a weak base will deprotonate it first. So you'll probably lose a point or two if you do that. But like if we had a weak base with an amine, it will deprotonate after the addition. But that's a good question. It's kind of a higher level concept, but it's a good thing to think about. Okay, so we got two more of these to go. Again, I got 3 carbons. I'm gonna chop this guy off because I can see kind of where I can go from there. My first thought would be some sort of enolate with a leaving group. That'd be pretty easy to form. Um, that would get us straight there. So then I have to continue breaking this down. I see that these two things are meta to each other. So there's actually this is actually trickier than I intended it to be, now that I'm looking at it. Okay, so we know that I could just have this with LDA gets me to that. So then I have to think about how I can get these two things on here and why I would possibly draw those in the wrong place. So how do I get these two things meta to each other? Well, this is clearly a meta director, so I'm going to think to cut this off. But one of the problems here is that probably the best way to add this would be to, so one of the ways you could think of adding this would be to add it like this and reduce that, right? That's definitely a possibility, but you run into an issue where do I reduce, which carbonyl do I reduce? So actually what's probably best here is to this is honestly probably the best answer. You might have a different answer that'll get you good partial credit, but I would say this is probably the best answer is to say this plus Br2 Fe Br3, doesn't matter what Lewis acid I use, would get me the meta substituted bromine. Then I could turn that into a Grignard like I was talking about earlier. Or actually, I wouldn't want to do that. Why I'm saying the Grignard works better is because you do run into this issue if you do it just the traditional way of having two different carbonyls. So I can protect this carbonyl first.
Isn't epoxide a meta director?
That's a good question. I don't know. I do not know. So you could add the bromine, then protect that carbonyl and do a Grignard with that aldehyde. So this ended up being a little bit more complicated than I meant it to be, but I still think it's a valuable thing to go through and to kind of see what you could do, kind of catch yourself, make sure that you're not putting two carbonyls with the same, reducing agent or something like that. And then just to get here would be H3O plus. So that might be the most reasonable way to do this. I think the key here is seeing that this enolate here, and then there's probably several different ways you can kind of make this happen, right? But this is what I thought of. So you brominate, turn it, protect the carbonyl, turn it into a Grignard, attack, and then deprotect it. Yeah, I'm at this point, I've just kind of started completely disregarding this format, which is fine as long as we know what you're doing. These kind of start getting in a place where like what is a major bond forming versus not major bond forming, which is fine, right? Like a traditional chemist doesn't necessarily think in those terms. I think it is helpful to kind of get a hold of what we're doing. But for some of these, it's just we're just doing chemistry. So again, I'm gonna break this guy down.
Quick question about the last one. Will do we need to break down each individual step, or can we combine them like you did at the bottom with one MG to all of that, or do we need to write them out as separate steps?
That's a good question. So what's hard about it is that there are times when you can do this, and those times are when everything can go in the same pot and it's fine. But like you guys don't have the experience to know that. So I'd probably just say be safe. And unless you see me do those two steps exactly together, don't just start like throwing a bunch of steps in the same. Don't start just doing 1, 2, 3, 4, 5. You know, like there are some things like the reductive amination, where like if you do the one amine, 2 LAH, totally fine. This like Grignard formation with the Grignard, totally fine. But I wouldn't like put one BR2 FeBr to protect the alcohol. Like there's sometimes where that's fine and sometimes where it's not. So I wouldn't just start doing it on your own. But that's a really good question. Here I see the ester. So I'm going to do this. Those are my two pieces. Done that before. These two things are, you know, para to each other. So there's, again, a couple different ways you can do this. One idea, you could potentially do something like this, where you had this bromine to do that. Whatever Lewis acid, right? That makes sense to do, and then you kind of run into this thing of trying to turn that carbonyl into that alcohol, which actually isn't too bad. You could also, in theory, form like do some sort of Grignard or something. But that also runs into its own issues. So we're gonna just run in, we're just gonna try this. So these two things are gonna make this and this, and I'll kind of show you what the kind of pain in the butt is. So we have to get here, right? So I'll just call this 1, and I'll go get more room down here from the mini synthesis. So 1, let's keep our thoughts organized. We already explained how we get this. And we want to get to an OH that's 2 carbons away from the benzene ring. So I need to make this a potential leaving group because I want to move carbons over. So this kind of goes back. Then I can use a strong acid and heat to do the elimination. And then the even this kind of runs into some issues, right? This would be the anti-Markovnikov addition. So there's some tricks here. The Grignard way actually might be a little bit cleaner, but I'll try to vet these before I put them on the actual test. But this is actually a good challenge, right? You run into some interesting issues, right? Like even this, like they're both, you know, they're both secondary carbons, so they're both gonna make secondary alcohols. So is that really anti-Markovnikov? Technically it is, but not for a reason you guys know. But yeah, these are good challenges. There's a couple different ways you can do them. I would challenge you to do them the way you think about doing them, and then send them to a TA, send them to an LA, send them to me, and we can look at them and be like, yeah, that's a good idea, or oh, it runs into a problem here. Okay, so yes, let's do this. So a couple people asked this. Let's talk about how we can make the acyl chloride because we forgot. So if I start here and I want the acyl chloride on the end, I need to first get an alcohol there. So that means I need to do the anti-Markovnikov OH addition. Then I need to get it all the way to the carboxylic acid. So I'm going to use the strongest oxidizing agent I know, which is this. But I don't want the carboxylic acid, I want the acyl chloride. And so there is a way I can substitute the OH out for a chlorine, and it's the SOCl2. So yeah, it's probably been a minute since you guys seen that, but this is kind of review. You guys had to do this, I think, on the second test, but yeah. Essentially, you oxidize it all the way to carboxylic acid, then SOCl2 will replace it with the chlorine. Yeah, I didn't show kind of how to make this. You're going to need to know how to make that, and things like I didn't show how to make that, right? Or yeah, even this. So you're on the test, you're going to have to show how to make that, but it's all the same steps. It's all going to be turn it into an alcohol, turn that into carboxylic acid, then SOCl2. All right, great question. Yeah, sorry I didn't talk about that. So this is spectroscopy. So the first thing I'm going to do is the degrees of unsaturation, 2 times carbons plus 2, all divided by 2. In this case, I don't have any nitrogens or halogens. Or sorry, minus hydrogens. So equals degrees of unsaturation. That tells me how many double bonds and rings I have. So I see 20 plus 2 minus 14 divided by 2. So that's, hold on. Am I doing this right? Yes. So that's 8 divided by 2 is 4. Okay, so that gives me a degree of unsaturation of 4. I see 4, I think benzene? Question mark? So that's validated because I see peaks around 7. So that tells me, yeah, I definitely have benzene. That's going to be in there. I look over here. I'm looking for a very obvious peak around 1700. Maybe this is it, but it looks really low. That's in the 1600s. Because I do have an oxygen, so I have to decide what it is. I don't see an obvious OH peak. So I'm not quite sure what's going on with this oxygen. If I have a benzene ring, well, then I can't have a carbonyl, right? Because I only have 4 degrees of unsaturation. And a benzene takes all 4 of those. So what am I doing with my oxygen? It's not an OH. Okay. So then I'm going to start building fragments. I see 6 hydrogen. I'm going to think my first thought is two CH3s, especially this since it's a doublet, that are symmetric because they're sharing the same carbon. So that's kind of a dead giveaway. That 6H, I might be dealing with that. Then I look at 1 hydrogen, so that would kind of go with this guy. Yeah, he has at least 6 neighbors. That would explain all of this splitting, right? So that seems like a viable fragment to me. And then I have this. So this is a CH3 with no neighbors. But something does kind of stand out. It's really far downfield. I mean, this is almost 4. So potentially, maybe this is an oxygen. That seems reasonable. So these seem like 2 pretty complete fragments. I can't go anywhere based off of them. And I've explained all of these peaks down here. Now I need to think about why benzene would have two hydrogen that are both doublets. Well, that tells me that's pretty indicative that I've para substituted. So one of these sides is going to be an isopropyl. The other side is going to be a methoxy. And that kind of ticks all of my boxes. So that's how I'd think about that. I would go step by step and say, I've got benzene. What does that benzene look like? Let me start building fragments. Let me see if I can put these fragments together. So I do think what most people would miss is either just assuming that there's a carbonyl here and forgetting that and like glossing over the degrees of unsaturation, or they would miss that, hey, this 3H is really far downfield. So that's probably connected to an oxygen if I had to guess. All right, so this would be 20 plus 2 minus 12 divided by 2. So that's going to be 5 degrees of unsaturation. Again, there's no like really obvious OH peak. This could be a carbonyl. I do have 1 oxygen and 5 degrees of unsaturation. So is this a carbonyl? Maybe, right? It's a possibility. All right, so I have 3 different 3H singlets. So a 3H singlet is going to look like that. Got 3 of them. Oops. I've got to figure out what to do with those guys. They've got no neighbors. They're, you know, they're just hanging out. Then I've got a benzene. Almost certainly, I've got multiple peaks up by 7. But I've got to decide how this benzene is substituted. Since I only have 3 benzene protons, that means that I have since I have 3 benzene protons, that means that there's 3 different things attached to them, attached to benzene. So that makes total sense. But how are they attached? So they could be attached. They could be attached 1, 2, 3, or they could be attached 1, 2, 3. Well, that's really the only 2 ways they could be attached. So what is it? How are they attached? So I'm just gonna put one of my methyls there. And then if it was like this, I couldn't possibly have a singlet, right? This would be a doublet, triplet, doublet. So the fact that I have a singlet probably tells me that I have something that looks like that, right? This carbon, one of these, this hydrogen has no direct neighbors. So that's the only way I could really have a singlet. So this looks pretty good to me. I've made a lot of ground, but I am missing my oxygen and my degrees of unsaturation. And having a carbonyl here actually makes sense because there'd be no direct hydrogens off of it. So we know that these are at the end because they're CH3s. They can't be in the middle of anything. So one of these has to be at the end of my carbonyl. To be honest, we don't know enough to know kind of which one of like where the carbonyl is out of the 3 of these. So I'd take any one of those 3 as the right answer. But that's just kind of how I'd think. So really the big things for me with the spectroscopy are, can you recognize a benzene? Can you recognize how benzene is split? Or like, yeah, what the different splittings are and what that tells me about what kind of substitution pattern I have on benzene. Can you start building fragments starting from my multiples of 3? So look at 3, 6, 9, start building fragments from there. If I have oxygen in my molecule, can I use an IR and other deductive reasoning to figure out if this is going to be an OH or a carbonyl or whatever? So those that's kind of what I'm thinking with spectroscopy. That's where my mind is going in terms of like what I think is important and how I'll test you on it. Okay, so that's the practice test. That's basically all of it. Do you guys have any questions I could answer about the final, about this test, about the final practice, about any of it?
How many questions are gonna be like on it?
I don't know. 6.
Is it also going to be on paper?
Yes. So it's gonna be on paper, scanned, and put onto Gradescope. So like you take the test on paper and then we're gonna put it on Gradescope. It's just gonna be like test 3. Honestly, it's
You
gonna look very similar to your previous tests. Like nothing's gonna be crazy different.
can you briefly summarize what we need to know about aromaticity?
I'm not gonna ask you about aromaticity. Like genuinely, if it's not here or something that I've talked about a lot, then it's not gonna be on the test.
Do you have like a turnaround time for like when you think the final grades will be in?
I mean, since it's the length of a test, I will say that like if you take the final early, it won't be necessarily graded sooner than everybody else. We're gonna just pull everything together. Um, so if that happens to be you where you're taking the final on Wednesday instead of Friday, like you don't get priority grading. I mean, hopefully Tuesday, Wednesday next week at the latest, it's in the grade book set.
Okay, thank you.
Yeah, it should be pretty similar to a normal time frame. So every test essentially they've gotten done grading around Tuesday. Tuesday early afternoon.
Quick question.
Yep.
In earlier, we were saying a stereo center was create. I know you said you'd be specific about how you ask for stereo centers, but in
Mhm.
like the one benzene where we created a negative charge, would that actually be a stereo center because it only had 3 bonds?
What are you talking about? Benzene.
Um, I let me find it because there was a problem where we were talking about creating a stereo center where we have this one where we have LDA basically attack a hydrogen that's next to a carbonyl, that one.
Mm-hmm.
And we were talking about it forming a stereo center on that bottom carbon there.
Yeah, the carbon on the cyclohexane.
Why could it be a
This
stereo
is
center if it's only bonded to 3 things
it's bound to 4 things.
with a negative charge? Oh, it forms it after. Okay. I misunderstood what was meant.
Yeah, this is a stereo center.
Okay. Okay.
Yeah.
Yeah.
Good question. Yes, you're right. This is not a stereo center where it's negatively charged, but as soon as it adds that other carbon, there's still a hydrogen
Oh,
here.
stereo
It's
center.
negatively
Got it.
charged. Or it's stereo center. Will we need to name every reaction, or will you specifically ask us to name them? Yeah, I'll make it clear when you do or do not need to name a reaction. Someone asked, will grades be posted on Canvas before they are officially reported to the registrar? Yes. So, what I'll probably do is as soon as the final grades go in, I'll make sure everything's set on the grade book, and I'll like on Canvas, everything will be set on Canvas. All of my settings will be right. I will have everything and I'll say, this is what I'm submitting to as the official grades. You know, you have a day to let me know if that's gonna be okay. Can we stop coming to class if we take the exam on Wednesday? The only other class would be final of Friday. So you do not have to sit in and watch other people take a test on Friday. Yes. Are you asking, can you stop coming if you're, can you miss Wednesday's class if you take the exam on Wednesday? I mean, it's a free country. I don't know what to tell you. Classes aren't required to come to.
Could you actually,
I would go, but I'm also, the one making class.
would you mind making an announcement post for the test time and place, like for Wednesday and Friday?
I already announced the test time on Wednesday. It's 3:30 in Croto Auditorium and CSL. That was in the announcement
CSL?
this weekend. And then Friday
But
is just regular class time.
what room would it be in?
It's in the Croto Auditorium.
Oh, okay.
Yes. Yeah, that should be in the announcement from this weekend.
On Wednesday, what's your plan for office hours? Is that going to be in a different location than your office, like by the Credo Auditorium, like in the normal LA review session room, or is that going to
No,
be
no, no.
normal?
So yeah, we will be doing the early test in the where the LA review is, right? But my normal office hours, we'll do office hours in the normal place.
Okay.
Yes.
Are you still doing office hours on Thursday?
That's the plan.
And no recitation, right?
Yeah, no recitation. I mean, sorry. I believe we still have recitation, but it's not required. There won't be like a quiz there. Um, Although maybe I'll just make it evil and just do the recitation, the one missing recitation that day, and make you guys show up. I won't do that, but I could. I'm within my rights to do that.
Dr. Little,
What's up?
for the extra 5 points that you mentioned in class that will be given, is that from the evaluation, the course evaluation, or is that something else?
Yeah, so I'll send you my own evaluation, and if you do that,
Okay,
you'll
so not the FSU one.
no.
Okay.
Although you should do that too. My
Yeah, I did.
I get raises and promotions based off of that. So if you could fill that one out and say nice things, if you have enjoyed the class, I guess. If you haven't enjoyed the class, then don't worry about filling out the thing. I mean,
Okay.
Dr. Little, when you say to use solvents to justify reactions, is that like recognizing DMF and DMSO will like help with SN2 reactions and speed up reactions and stuff
yeah,
like
just kind of
that?
like, you know,
Like aprotic,
so
you know.
I kind of misworded that, right? Like you use a solvent sometimes to kind of help a reaction, but it's usually you're using a solvent so it doesn't interfere with the reaction,
Okay.
right?
Thank you.
And so that's kind of more the thrust of the question.
Okay.
Yeah,
Will
good
you
question.
more so be like looking for us to recognize the solvents in the reactions, or will there be any like you have to fill in the blank type of solvent questions?
It's gonna be more like I give you a reaction, I ask you very specifically to tell me about the solvent.
And where would we find like more practice on that? Just the one lecture?
Um, yeah, it's not really about practice. It's a conceptual thing. I mean, I
I have a
guess
technical question.
the practice, sorry, yeah. Hold on, let me finish, Andrea. I'll get back.
Go ahead.
The practice would just be like, can you recognize protic and aprotic solvents? Can you recognize polar or not polar? Do you know enough about reactions to tell me why a protic reaction would be a problem, or not a problem?
Okay.
Yeah, I don't have more practice for that without just like giving you the test. Andrea, what's up?
So for the Lewis acid questions where like we have to see whatever's like electron drawing or electron withdrawing. I know that halogens are both, but you would prefer us to like recognize them as withdrawing groups, right?
So halogens are weird. Halogens are electron withdrawing groups, but they're orthopara-directors.
Oh, that's what it is. Okay.
Yeah, so for the purpose of this test, it's more that just use them as orthopara-directors. Because like we're
Okay.
just using them in synthesis, really. I'm not gonna be like, hey, I'm not gonna ask you about that.
Okay.
So at this,
If it is, then it's gonna be a leaving group, right?
what do you mean?
Like if you ask us like if a halogen is on a benzene and we have a Lewis acid and like a nucleophile, it's just gonna be an SN2, right?
No, if
Like
benzene's
it'll just
on,
leave.
it depends, right? If you have a leaving group on a benzene, and you pair it with a nucleophile, you're probably looking to do an SN2. You're probably looking to do an SNAR. But if it's paired with an
Okay.
electrophile, well, then we're not going to substitute out that electrophile with another
Right.
electrophile. That doesn't make any sense.
I have a
Okay,
question.
yeah.
Okay, level.
But if we're using um a Lewis acid, even in the presence of a alkyl bromide or aryl bromide, bromine on a benzene ring, like we're trying to use benzene as the nucleophile, not the electrophile.
Right.
So you're not going to be
Thank
replacing
you.
that bromine. Yeah.
May
What
I
about
ask a
aromatic
question?
things? Do we have to focus on it or just what you speak about in this practice test? If you can do what, I mean, this is the main thing, right? Can you do the reactions to make a synthesis? So I'm not gonna ask you the mechanism of an aromatic reaction necessarily, but can you use it practically in a synthesis? Sorry, someone else was speaking up.
Do you have advice when doing synthesis with benzenes, how we should add substituents, like when we should use a Lewis acid or try to form like a alkyl bromide on it?
Um, you know, generally you can do it both ways. Like you're saying like when to just, I mean, you're gonna have to do a Lewis acid even if you brominate it. But yeah, in general, as long as you get to the product, both ways kind of work. It
So
really
you,
depends on the question, and like there's no like one sentence like, hey, Grignards work better in these situations. Grignards might be a little bit more flexible, but sometimes you want to put that carbonyl on because it's a meta director, and to do a Grignard and then addition and then oxidize up to the ketone, that's a bunch more steps. So sometimes a Grignard's what you want to do. Sometimes you want that meta director, and it's easy to just put it on. The Grignard takes more steps usually, but you can do more with it.
Could you do two Grignards in this one?
I mean, yeah, if you wanted to. In this one, yeah, I mean, if you wanted to, you did this, you added the first bromine. Well, actually, not this one. This one doesn't work like that. But this one, right? Yeah, if you wanted to form this first guy with a Grignard, you could do that. It'd be more steps.
Dr. Little, knowing when the inversion of stereochemistry happens, is that like associated with SN2 reactions versus like racemic mixtures where two different products happen? Is that when like the final product has a chiral center, if that makes sense?
Wait, say that whole thing again.
Sorry, I know that was a lot. Knowing like the inversion of stereochemistry, like with certain reactions. Is that like often with just like SN2 reactions, like when, you know, sorry, there's not really an example on this. I don't know.
I mean, there
maybe.
is an example, right? Here's an example. This isn't an SN2, but it's just like an SN2, right?
Okay.
Right. In one step, you're attacking an electrophile and kicking it off. I mean, if I change that epoxide to a BR, it's the same things. It's just an SN2. So yeah, for full credit, if I give you stereochemistry, you should be looking to give me back stereochemistry, or at least justify why you wouldn't have stereochemistry. Right.
Okay.
In this case, that stays a chiral center every single step. So it's going to have some sort of chiral information. But in a lot of these, like that carbonyl isn't a chiral center. Now it is. So that's a chiral center, but there was nothing directing anything. And like, now this is no longer a chiral center. So it doesn't really matter, right? Nothing's chiral about this reaction.
Okay. Thank you.
Yep.
Hey, could you post the notes for lecture 26 and 27? I think somebody asked that in the chat.
Yeah, it's on my long list of things to do.
Also, for the extra credit thing, is it just like on Canvas we can do right now, or is it not until later?
Yeah, I'll open it up. I'll open it up probably tomorrow. Again, I've got to make that. Um, so yeah, I got a lot going on, so I'm working on it. Um, but yes, it will be up. It will be up for a couple of days. You'll have a minute to do it, and then that will come in before the final grades are tallied. Yes. Okay, so if no one has any other questions, I'm going to stop the recording.
I have a question.
Yeah,
What about the extra 5 credits thing? I didn't get it.
that's what I was just talking about. It's just gonna be a survey that I give you. And so if you do it, I'll give you a couple days to do it. If you do it, then you're gonna get 5 extra credit points. It's that easy.
Okay, thank you.
Yes, and I'll talk more about that on Wednesday.
Okay, perfect.
One more thing, for the 1,4 reactions, would majority of, like you said, enolates do the 1,4 preferred to like the 1,2?
Enolates do 1,4. Yes.
Okay.
Yep. Always, always. If you can do a 1,4 with an enolate, do it. Cool. Awesome.